There is a faint, ghostly smudge of light in the autumn sky, a hazy patch that ancient astronomers noted but could not explain. To the naked eye, it looks like a tiny, blurry star, but through a telescope it resolves into a soft, glowing oval. For centuries, this object was dismissed as a nearby cloud of gas, a nebula within our own Milky Way. But one man, sitting in his study in the quiet German city of Königsberg in the 1750s, looked at that same smudge and saw something revolutionary. Immanuel Kant, a philosopher by trade, proposed that this might be an island universe, a vast collection of stars as immense as our own galaxy, but so incredibly far away that it appeared as nothing more than a dim patch of light. Kant lacked any proof, and his idea was largely ignored. Yet his instinct was correct. The object he mused about is the Andromeda Galaxy, our closest major galactic neighbor, a colossal spiral of more than 1 trillion stars, and it is heading straight for us. Let's begin by stepping back and understanding where Andromeda actually sits in the cosmic landscape. It is located about 2.5 million light-years from Earth. That number is so large, it becomes almost meaningless. So let's reframe it. The light you see from Andromeda when you look up on a clear night left that galaxy 2.5 million years ago. That is a fossil beam of light, a messenger that began its journey before modern humans even existed. Our ancestors, the early hominins of the Pleistocene, were just beginning to walk upright when that light set out across the void. So, when you gaze at Andromeda, you are not seeing it as it is now. You are seeing it as it was in the deep past. That is the first key insight. All of astronomy is a form of time travel, and Andromeda offers one of the most dramatic examples. The story of how we came to understand what Andromeda truly is reads like a detective novel, and it hinges on a handful of brilliant, stubborn minds. The earliest known recorded observation of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi in the year 964 AD. In his book of Fixed Stars, he described it as a nebulous smear in the constellation of Andromeda, named after the mythical princess. But for more than 6 centuries, that was about all anyone knew. Then, in 1612, the German astronomer Simon Marius turned his telescope toward the same region and recorded it as a faint, extended glow. He is sometimes credited as the first telescopic observer of the galaxy. A few decades later, the French comet hunter Charles Messier added it as entry number 31 in his famous catalogue of fuzzy objects, marking it as something to avoid while searching for comets. Messier never knew that his catalogue would become a treasure map of galaxies. The real philosophical shift began with Kant. In 1755, he published a book titled Universal Natural History and Theory of the Heavens, in which he argued that the Milky Way was not the entire universe. He suggested that the spiral nebulae, as they were later called, might be other Milky Ways, entire galaxies of stars so remote that they appeared as tiny patches of light. Kant's idea was bold, but lacked observational evidence. Over the next century, astronomers like William Herschel and his son John Herschel made detailed sketches of these nebulae, noting that some, including Andromeda, showed a reddish tint at the center. William Herschel, based on his observations, guessed that Andromeda was the nearest of all the great nebulae, but he still believed it was a cloud within the Milky Way, and he estimated its distance at a mere 18,000 light-years. He was off by a factor of roughly 140. In 1845, the third Earl of Rosse, William Parsons, built a massive telescope in Ireland called the Leviathan of Parsonstown. With it, he resolved the spiral structure of the Whirlpool Galaxy, and soon after, he identified similar spiral arms in Andromeda. Yet even then, the consensus held that these were merely spiral nebulae inside the Milky Way. The idea that they might be separate galaxies remained fringe. The turning point came in the early 20th century, and it involved a violent stellar explosion. In 1917, American astronomer Heber Curtis was examining photographic plates of Andromeda when he noticed a nova, a star that had suddenly flared up, briefly outshining its surroundings. Curtis then scoured older photographs and found not one, but 11 more novae within Andromeda. Critically, these novae were all about 10 times fainter than the novae observed elsewhere in the sky. If Andromeda were a nearby nebula, its stars should appear at similar brightness to those in our own galaxy. But they did not. The only explanation, Curtis realized, was that Andromeda was enormously distant, so far that even its brightest eruptions appeared dim. He revived Kant's island universe hypothesis and proposed that Andromeda lay some 500,000 light-years away. This claim ignited a firestorm of controversy. In 1920, Curtis faced off against the leading Harvard astronomer Harlow Shapley in what became known as the Great Debate. Shapley had measured the size of the Milky Way and concluded it was around 300,000 light-years in diameter, which was actually an overestimate, but he believed that the entire universe was this size. To Shapley, the spiral nebulae were just gas clouds inside that sphere. He argued that if they were truly separate galaxies, they would have to be tens of millions of light-years away, a distance that seemed absurd to many. Curtis countered by pointing out the sheer number of novae in Andromeda, far more than could be expected from a simple nebula, and also noted dark lanes in Andromeda's spiral arms that resembled the dusty regions in the Milky Way. But the debate ended in a draw, with no decisive evidence either way. The deadlock was broken 4 years later by an astronomer working at the Mount Wilson Observatory in California. Edwin Hubble had access to the newly built 100-inch Hooker telescope, the most powerful in the world at that time. He focused on Andromeda and succeeded in identifying pulsating stars, known as Cepheid variables. These stars have a special property. The period of their pulsation is directly tied to their intrinsic brightness. By measuring how long each Cepheid took to brighten and dim, Hubble could calculate how bright it really was. Then, by comparing that intrinsic brightness to how faint it appeared from Earth, he could determine the distance. Hubble found that Andromeda was far more than 1 million light-years away, far beyond the bounds of the Milky Way. The Great Debate was settled. Andromeda was not a nebula. It was an entire galaxy, and the universe was filled with billions of such galaxies. That discovery, published in 1924, fundamentally reshaped our place in the cosmos. So now that we know Andromeda is our neighbor, what is it actually like? Let's take a journey, starting from Earth and heading toward it. First, we must leave our own galaxy. The Milky Way is about 100,000 light-years across. As we rise above its plane, the dense band of stars that dominates our night sky begins to thin. The light of billions of stars fades behind us, and the blackness of intergalactic space yawns ahead. Here, the emptiness is almost total. To give you a sense, on Earth, a cubic meter of air contains about 10 trillion atoms. Even in the vacuum of space near Earth, there are still about 1 million trillion atoms per cubic meter. In the vastness between stars, that number drops to around 1,000 atoms per cubic meter. But in intergalactic space, the density falls to just a few atoms per cubic meter. It is the emptiest environment we can imagine. And yet, it is not completely empty. Wandering through this void are rogue planets and stars that have been torn from their home galaxies by gravitational chaos. These exiles drift in perpetual darkness, their atmospheres frozen solid, their cores long dead, with no star to warm them. Halfway through our 2.5 million light-year journey, we begin to enter Andromeda's outer realm. Surrounding the visible galaxy is a vast halo of superheated plasma, expelled by past collisions and the energy of active star formation. This halo extends an incredible 1.3 million light-years from the center, more than half the distance between the Milky Way and Andromeda. Within this halo, we find Andromeda's retinue of satellite galaxies. More than 20 such companions have been identified, and many more may lurk hidden in the glare. The most famous are M32, M110, and M33, the Triangulum Galaxy. Each of these has played a role in shaping Andromeda's current form. Take M32. It appears as a small, bright blob of golden light in close-up images of Andromeda. It is a dwarf elliptical galaxy, only about 6,500 light-years across. But here is the mystery. M32 harbors a supermassive black hole at its center, with a mass of more than 1 million suns. That is far too massive for a galaxy its size. The best explanation is that M32 was once a much larger galaxy, perhaps a spiral, that had the misfortune of venturing too close to Andromeda. A close pass stripped away its outer stars, leaving only the dense core and its black hole. Today, M32 is a fossil of that violent encounter, a ghost of a galaxy that was devoured. Similarly, M110 is a larger elliptical satellite, about 17,000 light-years across. It too has interacted with Andromeda in the past. Astronomers have detected faint, metal-rich streams of stars in Andromeda's halo that appear to have been torn from M110 during a close pass. Imagine living on a planet in M110. Andromeda would loom in your sky, a vast, tilted spiral disk stretching from horizon to horizon. The historical and cultural implications of such a sight are staggering, a constant reminder that you are orbiting a doomed world destined to be absorbed. The third major satellite, M33, the Triangulum Galaxy, is a different case. It is a spiral galaxy in its own right, about 60,000 light-years across, and it may be a true satellite of Andromeda or simply a nearby independent galaxy. Regardless, the two have clearly interacted within the last few billion years. Computer simulations suggest that M33 will either be swallowed by the merging Milky Way-Andromeda system in the future, or be flung out of the local group entirely. Its 40 billion stars hang in the balance. Now, we finally reach the visible disk of Andromeda. The galaxy is classified as a barred spiral, similar to the Milky Way, but on a grander scale. Its visible component spans about 120,000 light-years, but when you include the extended disk of scattered stars from past collisions, the full diameter reaches some 220,000 light-years. Andromeda is the largest member of the local group, and it contains more than 1 trillion stars, compared to the Milky Way's estimated 100 to 400 billion. These stars are not uniformly distributed. The galaxy's spiral arms are complex, broken into segments by gaps where hydrogen gas accumulates and triggers bursts of star formation. In 1998, the European Space Agency's infrared telescope revealed that Andromeda's dust is arranged in multiple overlapping rings, suggesting it may be transitioning into a ring galaxy. Later observations with NASA's Spitzer Space Telescope showed two main spiral arms that extend from the central bar, but these arms are fractured into 7 distinct segments. At the boundaries between these segments lie giant star-forming regions. The largest of these is NGC 206, a cloud of gas and dust some 4,000 light-years across, home to more than 300 luminous blue supergiant stars, each dozens of times the size of our Sun. Andromeda also hosts an impressive population of globular clusters. We have identified more than 460 of them, more than triple the number known in the Milky Way. The most massive is Mayall 2, which contains several million stars of varying ages and metallicities. Curiously, Mayall 2 may not be a true globular cluster. Its diverse stellar population hints that it is actually the stripped core of a dwarf galaxy that Andromeda consumed. The outer layers of that dwarf were ripped away, but its core, held together by a black hole of about 20,000 solar masses, survived. Today, that black hole guides the cluster as it orbits Andromeda, a hidden relic of a cannibalized world. When we turn to the center of Andromeda, we find one of its most unusual features, a double nucleus. The core of the galaxy appears as two bright concentrations of light, designated P1 and P2. P1 is the brighter of the two, but it is offset from the true center. It is thought to be a dense cluster of stars orbiting around the actual nucleus. P2 lies at the center, and it contains the galaxy's supermassive black hole. This black hole is a monster, with a mass of about 100 million suns, around 25 times the mass of Sagittarius A, the black hole at the center of the Milky Way. Why the difference? Because Andromeda has been feeding for billions of years. As it absorbed other galaxies, their central black holes and gas clouds fell into its core, adding to the feast. The result is a gravitational behemoth that shapes the entire galaxy. Beyond the black hole, Andromeda is filled with the usual celestial denizens, neutron stars, black holes, and, very likely, planets. We cannot directly see exoplanets in Andromeda, but in 1999, astronomers detected a microlensing event called PA99N2, where the light of a red giant star in Andromeda was briefly brightened by the gravitational lensing of an intervening planet-like object. The data suggested a body about 6 times the mass of Jupiter. Though we cannot confirm that signal, it remains the best candidate for an extragalactic planet. Given the sheer number of stars in Andromeda, 1 trillion, and the fact that most stars in our galaxy host planets, it is almost certain that Andromeda is teeming with worlds. Some of those worlds may be Earth-like, orbiting sun-like stars in the habitable zone. But we may never know. Now, for the most dramatic part of our journey, Andromeda is moving toward us. When we look at its light, we see a slight blue shift, the opposite of the red shift seen in most galaxies. This shift tells us that Andromeda is approaching the Milky Way at about 110 kilometers per second. While the expansion of the universe pushes most galaxies apart, the local group is gravitationally bound, and Andromeda and the Milky Way are the 2 largest members. They are attracted to each other, and they will eventually collide. Now, a common fear when people hear about a galaxy collision is that stars will smash into each other. But that is a misunderstanding based on our everyday experience. Let's clarify why star collisions are extraordinarily rare. The key is scale. The average distance between stars in a galaxy is about 4 to 5 light years, and the Sun, for example, is about 1.4 million kilometers in diameter. That is a tiny fraction of a light year. If you scale the Sun down to the size of a cherry, the nearest star would be about 6,000 kilometers away. In such an empty environment, two galaxies passing through each other are like two swarms of dust particles. Almost all of the space is empty. The odds of any two stars physically colliding are astronomically low. In the entire merger of the Milky Way and Andromeda, with a combined trillion stars, only a few dozen direct star collisions might occur. The real danger to planetary systems comes not from collisions, but from gravitational interactions. Stars will pass close to one another, their gravity warping the orbits of planets, potentially flinging them into deep space or into their stars. The solar system, for example, could be ejected from the merged galaxy entirely, sent adrift in intergalactic space, or it could be pulled into the new galactic core. The timeline of this merger is well understood from computer simulations. In about 2 billion years, Andromeda will grow noticeably larger in Earth's night sky, eventually outshining the Moon. By 3 billion years, it will fill a huge portion of the sky, its light drowning out the view of other galaxies. By 4 billion years, the first contact will occur. The two galaxies will crash into each other, their spiral structures tearing apart. Stars will be thrown into new orbits. Gas clouds will collide, triggering bursts of new star formation. After the initial pass, the galaxies will swing back and forth, merging more with each swing. About 7 billion years from now, the two supermassive black holes at the centers will orbit each other, shedding energy through gravitational waves, and eventually merge into an even more massive black hole. The final product will be a giant elliptical galaxy. Astronomers have nicknamed this future galaxy Milkomeda, a combination of Milky Way and Andromeda. But Milkomeda will be the end of an era. After the merger, the available gas for making new stars will be largely exhausted. The galaxy will undergo a brief starburst, but then its star formation will fade. Over billions of years, the remaining stars will age, turning into white dwarfs, neutron stars, and black holes. The universe will continue to expand, pushing all other galaxies beyond the local group out of sight. Milkomeda will be alone, a fossil island in a vast dark void. Eventually, over tens of quadrillions of years, even the stars themselves will cool to near absolute zero, becoming dark, frozen spheres. The light of Milkomeda will go out, but that is an incredibly distant future. For now, we exist in the middle of this grand cosmic story. We are lucky to be alive at a time when Andromeda is still a bright spiral, when we can study it with telescopes and marvel at its beauty and complexity. We have only known that Andromeda is a separate galaxy for 100 years. In that century, we have mapped its stars, measured its black hole, watched its satellite galaxies, and predicted its fate. What will we learn in the next 100 years? Perhaps we will detect its planets directly. Perhaps we will send probes that can traverse the Gulf. Or perhaps we will simply continue to look up, as Al-Sufi did, as Kant did, as Curtis and Hubble did, and wonder at the faint smudge that holds so many secrets. Andromeda is not just a galaxy. It is a mirror in which we see our own past, our present, and our inevitable future. And so, as we end this journey, consider this. The light that left Andromeda 2.5 million years ago, carrying the image of a vibrant spiral, is now arriving at Earth. When it set out, our ancestors were just beginning to make the first stone tools. In another 2.5 million years, the light from a merged Milky will be traveling toward some distant observer. Whether anyone will be there to see it is a question that only time can answer. But for now, we are the witnesses. We are the ones who know that the universe is filled with islands of stars, and that among them, Andromeda is our nearest giant, our companion in the cosmic dance, our inevitable future neighbor. But let us press deeper, because the story of how we came to know Andromeda is as remarkable as the galaxy itself. Long before telescopes, before the Great Debate, before Hubble's decisive measurement, there were thinkers who dared to imagine that the Milky Way was not the entire universe. One of the earliest and most profound of these visions came from the German philosopher Immanuel Kant, writing in the mid-18th century. Kant had no telescope of his own, yet he reasoned from observation and logic. In 1755, he published a work titled Universal Natural History and Theory of the Heavens, where he proposed that the faint cloudy patches in the sky, what astronomers then called nebulae, might be island universes, vast collections of stars far beyond our own galaxy. He specifically pointed to the Andromeda Nebula as a candidate. Kant's idea was radical, even heretical. The prevailing view was that the Milky Way comprised the entirety of creation. But Kant had been inspired by the English astronomer Thomas Wright, who had earlier suggested that the Milky Way was a disk of stars, and that some nebulae might be similar disks seen from a great distance. Kant took this further, arguing that if the Milky Way were a disk, then other such disks must exist, and the Andromeda Nebula, with its elongated shape, must be one of them seen edge-on. He even speculated that these island universes would themselves contain planets and perhaps life. Kant's insight was a philosophical leap, not a scientific proof. Yet it planted a seed that would germinate over the next century and a half. Now, we must understand that the light we receive from Andromeda today is a fossil. It left the galaxy 2.5 million years ago, when our ancestors were just beginning to shape stone tools on the African savanna. That light has traveled through intergalactic space for more than 2 million years, carrying an image of Andromeda as it was then. When we look at Andromeda, we are looking back in time, and the galaxy may have changed dramatically in the interim. But we cannot see those changes. We are forever locked into a past view. This is a crucial point. The Andromeda we observe is not the Andromeda of today. It is a snapshot from the Pleistocene epoch, a deep-time fossil that we can never update. Every image from Hubble, every spectrum from ground-based telescopes, every radio map, all are messages from a world that existed before modern humans even evolved. This temporal disconnect is often overlooked, but it underscores the immense scales involved. The path from Kant's speculation to modern certainty was long and contentious. For most of the 19th century, the island universe hypothesis remained on the fringe. Astronomers like William Herschel, who built the most powerful telescopes of his era, believed that all nebulae were relatively nearby objects within the Milky Way. He even thought Andromeda was the closest of the great nebulae, estimating its distance at no more than 18,000 light-years, a gross underestimate. In 1845, William Parsons, The third Earl of Ross built the Leviathan of Parsonstown, a 72-inch telescope that revealed the spiral structure of some nebulae, including M51 and M99. He soon added Andromeda to the list of spiral nebulae, but he still considered them gaseous clouds within our galaxy. The idea that these spirals could be other galaxies seemed too fantastic. Then, in 1917, a discovery shattered the status quo. The American astronomer Heber Curtis, working at the Lick Observatory, was studying photographs of Andromeda when he noticed a nova, a star that had suddenly brightened. Nova events were known to occur within the Milky Way, but Curtis realized that the nova in Andromeda was far fainter than any Milky Way nova. If Andromeda were a nebula within our galaxy, the nova would have to be incredibly dim, which made no sense. Curtis searched historical photographs and found 11 other novae in Andromeda. He calculated that if these novae were similar to those in the Milky Way, their faintness implied Andromeda was at least 500,000 light-years away, far beyond the estimated size of the Milky Way. Curtis revived Kant's island universe hypothesis, but he faced fierce opposition, most notably from Harlow Shapley, a brilliant astronomer who had recently measured the size of the Milky Way using globular clusters. Shapley's Milky Way was enormous, about 300,000 light-years in diameter, and he believed it was the entire universe. He argued that the spiral nebulae were merely gas clouds within that vast realm. This clash of titans culminated in the famous Great Debate of April 27, 1920, held at the Smithsonian Museum of Natural History in Washington, D.C. Shapley and Curtis presented their arguments before a live audience. Shapley cited the observed rotation of the Andromeda Nebula. If it were a galaxy, its rotation would imply impossibly high speeds. He also pointed to a bright star in Andromeda that had been observed, which he thought was a nova that would place the nebula much closer. Curtis countered with the nova evidence, the dark lanes that resembled Milky Way dust clouds, and the fact that the spectrum of Andromeda resembled that of a star cluster, not a gas cloud. The debate was a draw. Neither convinced the other, but the scientific community was swayed by Shapley's reputation, and the island universe idea remained controversial. The resolution came 4 years later, thanks to Edwin Hubble. Using the newly completed 100-inch Hooker telescope at Mount Wilson Observatory, Hubble targeted Andromeda and other spiral nebulae. He was looking for Cepheid variable stars, stars that pulsate with a period directly related to their intrinsic brightness. By measuring the period of a Cepheid, you can determine its true luminosity. Then, by comparing that to its apparent brightness, you can calculate its distance. Hubble found Cepheids in Andromeda, and in 1924 announced that the distance was over 1 million light-years, far beyond the Milky Way's boundaries. Shapley was stunned, but the evidence was undeniable. The Andromeda Nebula was not a nebula at all. It was a separate galaxy, a vast island universe of stars. In one stroke, Hubble expanded the known universe 1,000-fold. The Great Debate was settled, and a new era of cosmology began. Since then, our understanding of Andromeda has deepened with each technological advance. Radio telescopes mapped its hydrogen gas. The Hubble Space Telescope, despite its name, has imaged Andromeda in exquisite detail, revealing individual stars and clusters. The Spitzer Space Telescope peered through dust to see its infrared glow, and the Chandra X-ray Observatory detected its black holes and neutron stars. Today, We know Andromeda's mass, its rotation curve, its star formation rate, and its chemical composition. We know that it has experienced multiple mergers, as evidenced by streams of stars in its halo. We know that its satellite galaxies, like M32 and M110, are remnants of those mergers. And we know that it is on a collision course with the Milky Way. But let's pause to appreciate the sheer emptiness that makes such a collision possible without stellar catastrophe. We already noted that star collisions are extremely rare. The space between stars is vast. To drive this home, consider that the Sun's nearest neighbor, Proxima Centauri, is 4.24 light-years away. If the Sun were a grain of sand, that grain would be about 4 kilometers from its nearest neighbor. Now imagine 2 clouds of sand grains, each containing hundreds of billions of grains moving toward each other. The grains themselves are so tiny and the gap so enormous that almost none will ever touch. That is the Milky Way and Andromeda. The galaxies themselves will tear each other apart, but the stars will simply pass through, their trajectories gently warped by gravity. The gas clouds, on the other hand, are much larger and more diffuse. They will collide, compress, and ignite waves of new star formation. That is why the merger will produce a brilliant starburst, but not a cataclysm of shattered worlds. Now, let us step back from the physics and consider the human dimension. When we look at Andromeda, we are looking at an object that has been known to our species for over 1,000 years. The Persian astronomer Al-Sufi recorded it in 964 AD as a nebulous smear. He had no idea what it was. The Chinese may have known it even earlier. For centuries, it remained a mystery, a faint patch of light that defied explanation. Then, in a span of a few decades, we transformed that mystery into knowledge. We measured its distance, its structure, its composition, and its fate. We discovered that it is not just a neighbor, but a twin, a mirror of our own galaxy. And we realized that our 2 galaxies are destined to merge, to become one. That merger will be the final chapter for the local group. The Triangulum galaxy, M33, will likely be pulled in as well. After 7 billion years, the supermassive black holes will unite. The new giant elliptical galaxy, Milkomeda, will dominate the local universe, but it will be a fading giant. Star formation will wane as gas is exhausted. The universe will continue expanding, pushing all other galaxies beyond the horizon. Milkomeda will be a lonely island, slowly dimming. Its stars will cool one by one until the last red dwarf fades to black. That will happen many trillions of years from now, but the process is already underway. And yet, for all that, Andromeda still captivates us. It is the only galaxy beyond our own that we can see with the naked eye. On a clear autumn night, far from city lights, you can look up and see a faint, elongated smudge. That smudge is 1 trillion suns. It is a history of mergers and collisions. It is a future merger with our own galaxy. It is a fossil light from a time before humans. It is a testament to the power of human curiosity. From Kant's philosophical speculation to Hubble's definitive measurement. We are privileged to live in an era when we can understand what that smudge truly is. So the next time you look at Andromeda, remember, you are seeing the past. You are seeing a galaxy that is racing toward us, a giant that will one day embrace the Milky Way. You are seeing 1,000,000,000,000 worlds, some perhaps bearing life, all silent and unknowable. And you are part of a species that dared to ask, what is that faint patch of light? And found the answer not in myth, but in science. The journey to Andromeda is not just a journey through space. It is a journey through time, through human discovery, and through the very nature of the cosmos itself. And we are only beginning. The faint light that has been streaming toward us for 2.5 million years carries a story of unimaginable violence. It began in the heart of a galaxy we call Andromeda, a vast spiral of 1,000,000,000,000 stars when a giant star reached the end of its life. In its final seconds, a cataclysmic chain reaction turned the star inside out. Trillions of tons of plasma, heated to hundreds of millions of degrees, erupted outward. Planets and moons that had orbited that star for eons were instantly vaporized, their matter scattered into a glowing cloud that expanded at a fraction of the speed of light. A shockwave of electromagnetic radiation, a pulse of pure fury, raced across the void in every direction. For millions of years, that pulse traveled through the emptiness between galaxies, slowing down not in speed but in intensity, until one night, in the year 1885, it finally reached Earth. That night, astronomers around the world looked up at a familiar fuzzy patch in the constellation of Andromeda, what they called the Andromeda Nebula, and saw something impossible. A new star had appeared, so bright that it momentarily outshone nearly every other star in the northern sky. It was a supernova, the first ever recorded outside our own Milky Way, though nobody at the time had any idea what it truly was. They called it S Andromedae. For 6 months, it blazed with a brilliance that defied all understanding. Then, as suddenly as it had appeared, it faded, and by the end of 1885, it had vanished back into the cosmic haze. Today, we know that supernova was just a glimpse of the enormous violent history that Andromeda has been hiding for billions of years. And yet, for all the attention we give to our own galaxy, Andromeda remains strangely overlooked. It is the closest major galaxy to us, visible to the naked eye from dark skies, and it dominates our local group of galaxies. So, why is it treated so often as a footnote? Why do we spend so much time exploring distant nebula while ignoring the Colossus right next door? Perhaps because it is so massive, so close, and so inevitable that we take it for granted. Or perhaps because its true nature is only now beginning to reveal itself, not as a serene twin of the Milky Way, but as a galaxy with a history of destruction so violent that it might be the most dangerous neighbor we could possibly imagine. Let's begin by correcting that oversight. Let's look at Andromeda not as a pretty picture in astronomy textbooks, but as a disaster waiting to happen, a galaxy that has already consumed dozens of its own children, that harbors unstable stars on the verge of detonating, that keeps a supermassive black hole hidden behind a double heart, and that is on a direct collision course with everything we know. 103 years after the 1885 supernova faded away, astronomers finally located its remnant. Using the most powerful telescopes of the time, they spotted a tiny dark patch near the center of Andromeda, a small nebula, barely distinguishable against the blinding glow of the galactic core. Spectral analysis confirmed it. This was the leftover debris of S Andromedae, a star that had exploded nearly a century before our great-grandparents were born, in a galaxy so far away that the light took 2.5 million years to reach us, was finally identified. But that identification raised more questions than it answered. Why did S Andromedae behave so oddly? Most supernovae either fade gradually or leave behind a pulsar or black hole that can be detected for thousands of years. S Andromeda vanished almost completely. Its remnant is barely a whisper in the radio spectrum. Some researchers believe that the supernova was a rare type of explosion, perhaps a low-energy or electron capture supernova. But without more data, the mystery persists. And it's only one of many that Andromeda keeps locked in its core. When we look at the center of Andromeda, we see something that should not be possible. It has a double nucleus, not a single bright core, but two distinct lumps of light separated by a few light years. The brighter, larger clump is offset from the true geometric center of the galaxy, and it contains hundreds of millions of stars packed into a region just 7 light years across. The second clump is dimmer and smaller, only about 1 1/3 light years wide, and it sits much closer to the heart of the galaxy. Astronomers believe that this second clump might actually be the true center, the place where Andromeda's supermassive black hole resides. That black hole is a monster. It has a mass estimated at around 50 million times that of our Sun. To put that in perspective, the black hole at the center of the Milky Way, Sagittarius A, is only about 4 million solar masses. Andromeda's black hole is more than 10 times heavier. But why does it hide behind a double nucleus? There are two main theories. The first is that Andromeda once swallowed a smaller galaxy, and the brighter clump of stars is the stripped core of that victim, still orbiting the black hole. The second theory suggests that the double nucleus is an illusion, created by a ring of opaque dust that blocks part of the light, making it look like two separate structures. Neither explanation is fully satisfying, and new observations from the Hubble Space Telescope and ground-based adaptive optics have only deepened the puzzle. The motion of stars near the center suggests there might even be a second, smaller black hole lurking there, a remnant of still another merger. The center of Andromeda is a graveyard of consumed galaxies, but the destruction does not stop at the black hole. In the same region, orbiting just a few light hours from the core, there is a star system that should not exist. It is almost invisible in optical light, but when you look at Andromeda in X-rays, this system blazes like a beacon. It is the brightest X-ray source in the entire galaxy. It goes by a tongue-twisting catalog name that you can see on your screen now. But to understand it, we need to think about what it actually is. One component is a neutron star, the collapsed core of a star that went supernova billions of years ago. This neutron star is small, only a few dozen kilometers across, but it spins once every 3 seconds, dragging a powerful magnetic field with it. The other component is a red giant star, much larger but much dimmer. They are so close together that every 4 hours, the red giant passes in front of the neutron star, eclipsing its X-ray glow. That close proximity means that the neutron star is slowly, relentlessly stealing matter from its companion. It is a cosmic vampire. Over tens of millions of years, the neutron star will continue to feed. It will pull gas from the red giant's outer layers, heating it to millions of degrees and flinging X-rays into space. Eventually, the red giant will be torn apart by tidal forces. Its material will form a hot, luminous ring around the neutron star, a beautiful but violent nebula marking the death of one star and the transformation of another. This system is a ticking clock, a preview of the cannibalistic processes that govern the evolution of entire galaxies. And it is not alone. All around Andromeda's core, there are millions of stars packed into a bulge that is roughly 12,000 light-years across. That bulge is unusually elongated, and it is connected to a massive bar of stars that stretches for nearly 180,000 light-years. The bar is so oriented that from Earth we see it almost head-on, which is why it is so difficult to detect. But its gravitational influence shapes everything that happens in the inner half of the galaxy. About 30% of Andromeda's entire mass is concentrated in that central region. The rest is spread out along two magnificent spiral arms that coil outward like a cosmic hurricane. Those arms are studded with dark dust lanes and bright stellar nurseries, regions where new stars are born. They are also home to some of the most unstable and dangerous stars known to science. One of them is a star called AE Andromedae. It belongs to a class of objects known as luminous blue variables, massive, hot, and utterly unpredictable. These stars are rare. Only a few dozen are known in the entire universe. Their surfaces roil with immense energy. They can fluctuate in brightness by factors of 10 or even 100, seemingly at random. And every now and then, they produce a flare so powerful that they briefly outshine entire clusters of stars. The most extreme of these flares is called a supernova imposter, because it looks almost exactly like a supernova but does not destroy the star. For a short time, the star's luminosity increases by millions of times, and then it settles back down, waiting for the next explosion. AE Andromedae is one of the brightest stars in its galaxy. Its mass is somewhere between 50 and 120 times that of our Sun, and at its maximum size, its radius is about 55 times the Sun's radius, nearly the size of Mercury's orbit. Its surface temperature hovers around 20,000 Kelvin, and its total luminosity is 500,000 times that of the Sun. It generates a stellar wind so powerful that it blows away 2 quadrillion tons of matter every second. That is a loss equivalent to 10 Earths every year, and yet, for a star of this mass, it is barely a drop in the bucket. The star will die long before that wind makes a noticeable dent. AE Andromedae is only about 2 million years old. By the standards of ordinary stars like our Sun, that is infancy. But for a blue giant, it is already most of its life. Within the next million years, a blink of an eye in cosmic time, it will collapse and explode as a supernova. When it does, it will leave behind a black hole and a nebula of debris that will glow for tens of thousands of years. The question is not if, but when. And if we were unfortunate enough to be aligned with that explosion, the gamma rays and high-energy particles could do serious damage to any life that might exist in the Andromeda galaxy. Fortunately, we are far enough away that Earth is safe from any local supernovae in Andromeda. But the star's impending doom is a reminder that this galaxy is not a quiet place. It is a factory of destruction. Speaking of destruction, let's talk about the past. Andromeda has a long and violent history of swallowing its neighbors. Throughout its existence, it has absorbed more than 100 satellite galaxies. Most of them were small and left little trace. But some were large enough that their remnants can still be seen as giant streams of stars stretching across the galactic halo. The most spectacular of these past collisions involved a galaxy that we now call M32. M32 is a small, compact, elliptical galaxy that orbits Andromeda at a distance of about 177,000 light-years. Its diameter is only about 8,000 light-years, but its mass is surprisingly large, about 1 billion solar masses. At its center is a supermassive black hole with a mass of 2.5 million suns, which is far too heavy for such a small galaxy. That is because M32 is not a normal dwarf galaxy. It is the remnant of a much larger galaxy that was nearly destroyed when it passed straight through Andromeda's disk about 800 million years ago. Data from the Spitzer Space Telescope revealed the evidence. A gigantic hole in one of Andromeda's spiral arms. That hole was punched by the intruder galaxy as it plunged through the disk at high speed. The collision stripped away most of the intruder's stars, leaving behind only the dense core. What we see today is the leftover heart of a once great spiral or elliptical galaxy. M32 is a ghost, a zombie galaxy that will never recover, and yet it still orbits Andromeda, doomed to eventually merge completely, adding its black hole to the growing monster at the center. Andromeda has about 30 other satellite galaxies, the brightest of which is M110, which is about 15,000 light-years across. Most of the others are faint dwarf spheroidals, barely more than a few million stars each. They form a loose swarm around the giant, slowly being drawn in. Over the next few billion years, many of them will be tidally disrupted and absorbed, adding their mass to Andromeda's halo. This is a natural process of galaxy growth, but it is not peaceful. It is a cosmic meal that happens one victim at a time. And then there is the biggest disaster of all, the future collision between Andromeda and the Milky Way. We have known for decades that Andromeda is moving toward us. It is approaching at a speed of about 300 kilometers per second. At that rate, it will take about 4 billion years for the two galaxies to meet. But the details of that meeting are far more complicated than a simple head-on crash. Recent simulations have shown that the collision will be a messy, drawn-out affair. Andromeda and the Milky Way are both spiral galaxies, and they are roughly equal in mass, though Andromeda might be slightly heavier. When they first make contact, their immense gravitational fields will begin to distort each other. The outer reaches of both galaxies will be stretched into long tidal tails. Stars that were once part of the Milky Way will be flung into space, and the same will happen to Andromeda's stars. After the first pass, the two galaxies will separate, only to be pulled back together again. They will swing around each other for another few 100 million years, merging more with each pass. Eventually, after several such orbits, they will coalesce into a single giant elliptical galaxy. All traces of the original spiral structures will be erased. The new galaxy, sometimes nicknamed Milkomeda, will be a sprawling, amorphous ball of stars with an enormous halo of globular clusters and diffuse light. But the question that keeps coming up in audience discussions is whether the collision will be a full merger or something less dramatic. Will the two galaxies simply pass through each other with minimal disruption? Or will they truly merge into one? The answer, based on the most recent data from the Hubble Space Telescope and the Gaia spacecraft, is that a full merger is almost certain. The tangential velocity of Andromeda relative to the Milky Way is very small. It is coming almost directly at us. The uncertainties are small enough that the collision is not just possible, but inevitable. The only real question is the timing. It could happen as early as 3 billion years from now, or as late as 5 billion. But when it does, There will be no avoiding the outcome. What will that mean for our solar system? The Sun will still be on the main sequence at that time, though it will be brighter and hotter than it is today. But the Earth will face a more immediate threat. During the merger, the gravitational interactions could perturb the orbits of planets. There is a small but non-zero chance that our solar system could be ejected from the combined galaxy entirely, flung into intergalactic space. More likely, we will end up somewhere in the outer regions of the new elliptical galaxy, far from the center. The night sky will be radically different. Instead of a band of the Milky Way, we would see a diffuse glow in all directions, with some regions brighter than others. But there is another, more profound disaster lurking in that merger. When two supermassive black holes, one from each galaxy, meet, they will begin to orbit each other. Over millions of years, they will lose energy by flinging stars out of the center, spiraling closer and closer. Eventually, they will merge, releasing an enormous burst of gravitational waves that will ripple through the universe. That event will be one of the most energetic since the Big Bang. Although it will not pose a direct danger to Earth, it will be a spectacular grand finale to the merger. So, why has Andromeda been so ignored in popular culture and even in scientific media? Part of it is the sheer scale of the galaxy. It is so big that it fills the field of view in a telescope, and its details are overwhelming. Another part is that it is not our home. The Milky Way is the galaxy we live in, so it gets the most attention. Andromeda is often treated as a kind of twin, but a twin that stays in the background. Only in the last few decades have we started to realize just how different it is. Previously, astronomers assumed that Andromeda was a near-perfect analog of the Milky Way, a spiral galaxy with a similar mass, similar star formation rate, and similar dynamics. But new observations have revealed that Andromeda's star formation has been much more intense in the past. It experienced a burst of star formation about 2 billion years ago that produced an entire generation of blue giants. That burst was likely triggered by a merger, possibly with M32. The Milky Way, by contrast, has had a relatively quiet recent history. Also, Andromeda's halo is much larger and more complex. It contains vast streams of stars that are the remains of multiple previous mergers. The Milky Way has similar streams, but not as many. Andromeda has about double the number of globular clusters, around 460 compared to the Milky Way's 150. These clusters are some of the oldest objects in the universe, and their abundance suggests that Andromeda's early history was incredibly violent. There is also the mystery of dark matter. Andromeda seems to have less dark matter relative to its visible mass than the Milky Way does. That was a surprise, because dark matter is thought to be the scaffolding on which galaxies form. If Andromeda has less, it could mean that its formation was dominated by mergers that redistributed the dark matter, or that our measurements are incomplete. Either way, it challenges our understanding of galaxy evolution. And then there are the planets. The first exoplanet candidate ever detected in another galaxy is in Andromeda. It is called Mega ML7b, and it is a gas giant about 6 times the mass of Jupiter, orbiting a red dwarf star. The detection was made using microlensing in 1999, and it remains unconfirmed because the star is so faint and far away. But if it is real, it means that planets are common even in other galaxies. And if planets are common, then the potential for life and the potential for disaster extends exponentially. Consider the habitable zone of Andromeda. The The central region is too crowded, too radioactive, and too gravitationally unstable for life as we know it. The outer regions are too poor in heavy elements to build rocky planets. Only the middle region, a band roughly 10 to 50,000 light-years from the center, might be suitable. And that is exactly where we might expect to find civilizations, if they exist. But those civilizations would have to contend with the same destructive forces that we face: nearby supernovae, gamma-ray bursts, galactic mergers, and the eventual death of their star. Andromeda may be beautiful, but it is also a factory of doom. Let's not forget the most mysterious object in Andromeda, a system known as RX J042.3 plus 4115, an X-ray binary that has been observed to flare unpredictably. In 2006, it suddenly became one of the brightest X-ray sources in the sky, then faded again. Some think it could be a microquasar, a stellar mass black hole that is flinging jets of material at near light speed. Others think it might be an intermediate mass black hole, a rare and elusive class of objects that are thought to be the seeds of supermassive black holes. Whatever it is, it reminds us that Andromeda still holds secrets we cannot explain. So, where does that leave us? Andromeda is not just another pretty spiral. It is a living, breathing, violent machine. It is a galaxy that has been through war after war, consuming its children, ripping apart its neighbors, and now it is coming for us. The collision with the Milky Way will be the final disaster, but it will also be the beginning of something new. A new galaxy will form, and in that galaxy, the sun will continue to burn for a few more billion years if it survives the chaos. We cannot stop the collision. We cannot prevent Andromeda from tearing apart our home, but we can understand it. We can watch it with our telescopes and marvel at its complexity. We can ask the questions that our ancestors could not. What exactly is the double nucleus? How many galaxies has Andromeda eaten? Will the black holes merge during our lifetime? And if there is life out there, in some quiet star system in Andromeda's habitable zone, are they looking back at us, wondering if we are coming for them? As the light from the 1885 supernova fades into memory, and as the X-ray pulses from the neutron star continue their steady beat, Andromeda keeps moving. It is not an object, it is a process, a slow-motion disaster spanning billions of years, and we are privileged to be the first species in the history of Earth that can witness it, understand it, and name it for what it truly is, the greatest show in the universe and the most spectacular catastrophe that will ever befall our island of stars. In the end, when the merger is complete, when the two supermassive black holes have spiraled together and the last star streams have settled into the elliptical glow, the light from that collision will travel across the cosmos for billions of years to come, and some distant observer, somewhere in another galaxy, will look up and see a new spot of light that was not there before. They will wonder what it is. They will never know that it is the graveyard of two civilizations, two galaxies, two families of stars, and that from their ashes, something new and beautiful was born. That is Andromeda's disaster, and it is ours as well. And yet, for all the destruction that Andromeda has witnessed and will cause, there remains a profound mystery that sits right at its very heart, a mystery that has puzzled astronomers for decades and still resists a simple explanation. That mystery is the double nucleus. When we look at the center of Andromeda, invisible light, we do not see a single brilliant point, but two distinct peaks of brightness. The brighter one, is offset from the true geometric center by a few light years. The dimmer one sits closer to the center. They are separated by only about 5 light years, which sounds enormous, but at the scale of a galaxy, it is like 2 grains of sand pressed together. For years, astronomers debated what could cause such a bizarre structure. One theory proposed that Andromeda once consumed a smaller galaxy, and the brighter nucleus is the remnant of that victim's core, still glowing after billions of years. Another theory suggested that a dense ring of opaque dust bimexed the center, creating an illusion of 2 nuclei, when in fact there is only one. But as telescopes improved, so did the data. The Hubble Space Telescope, with its sharp vision, revealed something even stranger. The brighter nucleus is not a single cluster of stars. It is a flattened disk of hot, young stars orbiting something unseen. And that something is almost certainly a supermassive black hole. The dimmer nucleus, meanwhile, is a separate, denser cluster of older stars. They appear to be 2 distinct objects caught in a slow cosmic dance. The leading hypothesis today is that Andromeda did indeed swallow a smaller galaxy, and the brighter nucleus is the former core of that galaxy, now being torn apart by the black hole's immense gravity. In a few million years, it will be completely disrupted, and the double nucleus will vanish, leaving only a single bloated core. But there is a deeper question. What exactly is the black hole at the center of Andromeda? We know from the motion of stars near the nucleus that it has a mass of about 100 million suns, roughly 25 times more massive than the black hole in the Milky Way. That makes it one of the largest supermassive black holes in the local group, yet it is surprisingly quiet. Unlike the active galactic nuclei we see in other galaxies, Andromeda's black hole emits very little radiation. It is a sleeping giant, but it will not sleep forever. When the Milky Way merges with Andromeda, the 2 black holes will begin to interact. The Milky Way's black hole, with a mass of about 4 million suns, will be a mere mouse compared to Andromeda's monster. But together, they will create a gravitational dance that will reshape the center of the new galaxy. And that dance is not just a spectacle. It is a process that could fling stars right out of the galaxy. As the 2 black holes orbit each other, they will exchange energy with nearby stars. Some stars will be accelerated to enormous speeds, becoming hypervelocity stars that streak into intergalactic space. Others will be swallowed entirely, adding mass to the black holes. Over millions of years, the orbits will shrink due to gravitational wave emission, and eventually, the black holes will merge. That merger will release a burst of gravitational waves so powerful that it will momentarily outshine all the stars in the universe combined in that frequency band. Even today, with advanced detectors like LIGO and Virgo, we cannot yet detect such a distant event, but future observatories may pick up the faint ripples from that final catastrophe. Let's step back for a moment and consider the timeline. The Andromeda Galaxy is currently about 2.5 million light-years away. That distance is closing at 300 kilometers per second. But that is not the only motion. Andromeda also has a sideways velocity. For a long time, astronomers were unsure whether that sideways drift was enough to make the 2 galaxies miss each other. But in 2012, the Hubble Space Telescope made precise measurements of Andromeda's motion across the sky. The result was clear. The sideways velocity is very small. Andromeda is coming straight at us. The collision will happen. The only question is exactly when. The best current estimate is about 4.5 billion years from now, with an uncertainty of about 1 billion years either way. But here is a detail that many people miss. The Milky Way and Andromeda are not the only major galaxies in the local group. There is also the Triangulum Galaxy, M33, a smaller spiral about half the size of the Milky Way. Its fate is less certain. Some simulations suggest that Triangulum might swing in and merge with the Andromeda Milky Way system early on, or it might be flung out into intergalactic space. It could also be torn apart by tidal forces. The outcome depends on the precise geometry of the encounter. So, the collision we think of as a binary event is actually a three-body problem. And three-body problems are notoriously chaotic. But for the Earth, the most immediate threat from Andromeda's approach is not the merger itself. It is the fact that the Sun will be dying around the same time. In about 5 billion years, the Sun will begin to swell into a red giant, expanding past the orbit of Mercury and possibly Venus. By the time Andromeda arrives, Earth may already be a roasted, airless rock. So the two disasters, galactic merger and solar death, will coincide. The night sky of a future Earth, if any life remains, will be a surreal vista, a swollen red sun dominating one side, and the vast approaching arms of Andromeda tearing across the heavens on the other. Yet even before that, Andromeda is already affecting us in subtle ways. Its gravity is pulling the Milky Way toward it, distorting our galaxy's outer halo. Some of the high-velocity stars we observe in the Milky Way may have been stripped from Andromeda's outer regions by tidal forces, and the leading edge of Andromeda's halo may already be touching the halo of the Milky Way. We are not just watching a distant disaster, we are already feeling its first tremors. Why then has Andromeda been ignored for so long in popular culture? Part of the answer is that it is too big to see easily. Its angular size on the sky is 6 times the width of the full moon, but its surface brightness is so low that you need a dark sky and averted vision to even notice it as a fuzzy patch. It does not appear in city light-polluted skies, so most people have never seen it. And when astronomers do study it, they are often overwhelmed by its complexity. Every new image reveals thousands of globular clusters, hundreds of star streams, and dozens of dwarf galaxies in its vicinity. It is a treasure trove of data, but it is also a nightmare to model. Another reason is historical. For much of the 20th century, Andromeda was considered the nearest spiral galaxy, but observations beyond the local group focused on more distant galaxies that showed active nuclei, quasars, and other dramatic phenomena. Andromeda seemed too calm, too normal. It was relegated to being a calibration tool for distance measurements. Only in the last 2 decades have we begun to appreciate its violent past and its unique properties. Take its globular clusters, for example. Andromeda has about 460 confirmed globular clusters, compared to the Milky Way's 150. And many of these clusters are incredibly massive. Some contain over 1 million stars. But unlike the Milky Way's clusters, which are mostly metal-poor and ancient, Andromeda's globular clusters show a wide range of metallicities and ages. That suggests that many of them were captured from smaller galaxies that Andromeda absorbed. They are orphans, homeless wanderers that have been adopted by a violent parent. One of the most intriguing clusters is G1, also known as Mayal 2. It is the brightest globular cluster in the local group, visible even in amateur telescopes under good conditions. Its mass is about 10 million suns, making it a candidate for a stripped dwarf galaxy core. In fact, it might be the leftover nucleus of a galaxy that Andromeda destroyed long ago. If confirmed, that would mean that G1 contains its own intermediate mass black hole. And there are hints that it does. X-ray emissions and unusual star motions have been detected. So, even in the quiet halos of galaxies, the seeds of destruction are sown. Now, let's talk about the star that started it all in this script, the supernova of 1885, known officially as SN 1885A, or S Andromeda. It was the first supernova ever observed outside the Milky Way, and it remains a puzzle. It was a type Ia supernova, which means it originated from a white dwarf that accreted matter from a companion star until it reached the Chandrasekhar limit and detonated. But the light curve of SN 1885A was strange. It faded much faster than typical type Ia supernovae. Its spectrum was also unusual, showing strong absorption lines of iron and calcium, but weak silicon lines. For decades, astronomers thought it was an anomaly. Then, in the 1990s, new models suggested that SN 1885A might have been a super Chandrasekhar explosion, where the white dwarf exceeded its normal mass limit before exploding. That would explain the rapid decline and the strange spectral features. But the problem is that such explosions are rare. Only a handful have been observed in modern times. So the 1885 supernova is not just a historical curiosity. It is a critical clue to understanding how some of the most important stellar explosions in the universe work. And yet, because it happened so long ago, our data on SN 1885A is limited. We know its approximate location, about 16 arcseconds from the nucleus of Andromeda. We know it reached a peak magnitude of about 6, visible to the naked eye on dark nights. We know it faded in 6 months. But we do not know the exact mass of the progenitor, the nature of its companion, or why it was so different from other type Ia supernovae. This is a perfect example of how much we still don't know about Andromeda. What about the neutron star system we discussed earlier? That X-ray binary, designated RxJ042.3+4115, is just one of many such systems in Andromeda. In fact, because Andromeda is so large, it contains tens of thousands of X-ray binaries, black hole candidates, and neutron stars. Some of them are pulsing, some are flaring, some are eclipsing. They form a cosmic zoo of extreme physics. And because they are at a known distance, they serve as laboratories for studying accretion processes, magnetic fields, and the final stages of stellar evolution. But beyond the individual objects, there is the enigmatic dark matter distribution. As mentioned earlier, Andromeda seems to have less dark matter than the Milky Way relative to its visible mass. That finding came from measuring the rotational speeds of stars and gas in the outer disk. In a normal spiral galaxy, the rotation curve remains flat or even rises far from the center, indicating a massive dark halo. For Andromeda, the rotation curve actually declines slightly at large radii, implying a lower dark matter fraction.
What if the colors we see in the night sky are just the beginning of a story yet to be told? Our documentary invites you on a journey of discovery, where each chapter unfolds the hidden narratives of distant worlds, challenging what we thought we knew about our universe. First, we dive into the azure depths of Neptune, revealing its true colors. A world far beyond our own, where the winds howl with ferocity and the skies tell tales of ancient ice and gas. What mysteries does this distant giant hold in its cerulean hues? Then we venture to the enigmatic Saturn, where atop its North Pole, a geometric marvel, the hexagonal storm defies explanation. What forces of nature sculpt this bizarre phenomenon? Can we unlock the secrets of Saturn's hexagonal riddle? Our odyssey continues as we seek the latest real images of Uranus. This elusive ice giant, shrouded in mystery, reveals new truths through the eyes of modern exploration. What will we discover in the unseen details of its atmosphere and rings? Finally, we journey with Chandrayaan-3 to our celestial neighbor, the Moon. Here in the silence of the lunar surface, the mission uncovers sights unseen by human eyes. What did Chandrayaan-3 witness on the Moon? What secrets lie in the dust and craters of our closest companion in space? Join us as we traverse the cosmos seeking answers and marveling at the beauty of the universe. This is not just a journey through space, it's an exploration of the unknown, a quest for knowledge, and a tribute to the human spirit's unending curiosity. Welcome to our documentary series, where the mysteries of the universe unfold before your eyes. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our Sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its dynamic atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was portrayed as a dark blue world whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions rather than the planet's true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with the Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to unravel with the advent of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue. but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs. The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes such as Hubble and the Very Large Telescope played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus and, by extension, Neptune with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity, in stark contrast to the relative calm of its stellar neighbor Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hotspots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the Sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the Sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which were affected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the Sun, create the overall appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color in visible wavelengths caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam, near-infrared camera, Neptune does not appear blue, in contrast to the darkened appearance one would expect due to methane absorption of light. In infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the Moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light in the form of water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they diverge in different directions, instead of just going straight through. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climatic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. Discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. Saturn has captivated the human imagination. From ancient civilizations to modern astronomers, the Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a parero, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery. It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps, such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Titan and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics? And perhaps even its potential for the existence of life. An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target for the search for extraterrestrial life. But the question remains, What would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Titan. It's an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle, it's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1 million miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During a long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics, They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan-3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the moon's south pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. the landing module's onboard systems were hard at work analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the moon's south pole, Chandrayaan-3 began its mission of exploration and discovery. So, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the moon, and it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrayaan-3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity, it's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters at the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's south pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The Lupex rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with Lupex, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like Lupex and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos.